Welcome to my presentation about automated defect inspection in reverse engineering of integrated circuits. My name is Ann-Christin Bette and I'm an external PhD candidate at Infineon Technologies and academically supervised at the Technical University of Munich. In the next few minutes, I will give you a brief insight into reverse engineering at Infineon, as well as some details about the methods and results of our proposed defect inspection framework. Circuit extraction is a complex chip-destructive procedure to gain knowledge about the microcontroller functionality. For this purpose, a few nanometer-sized structures can be extracted and analyzed. Of course, such a time-consuming and costly procedure is only used for certain questions that cannot be sufficiently answered by less invasive methods. Typical objectives include detecting intellectual property infringements as well as investigating the product integrity. Now, let's dive a little deeper into the circuit extraction process. The failure analyst expert on the left side has the task of assessing and digitizing the required structural information on the chip. For this purpose, he polishes the chip down to the level of interest and images the structural information with a scanning electron microscope. The resulting image mosaic, which often consists of thousands of high-resolution individual frames, is now passed on to the reverse engineering expert. This expert extracts the structural information using image processing methods and assembles the individual parts into an interpretable netlist. While the image is still being captured, our defect inspection tool comes into play. Based on the image mosaic, the application outputs a defect report that shows artifacts caused by polishing and imaging. The report serves as direct feedback for both experts. The failure analysis expert receives feedback on the status of his chip preparation. The reverse engineering expert receives automatic feedback on the areas that need to be corrected manually. We have composed a dataset of metal layers from 4 different technologies with over 64,000 images. We also defined 4 defect classes that are relevant due to the constant technology shrinking. We cut the original high-resolution images into 250 pixel square sections and labeled them. In this way, we obtained an imbalanced dataset on which several defects per image are visible at the same time, so we performed a multi-label classification. As a first approach, we trained an exception network initialized with ImageNet weights and with 4 output neurons, 1 neuron per defect class. As a second approach, we trained 4 individual binary networks, 1 network per defect class. In the first version, we initialized it with ImageNet weights, and in the second version, we used the already trained weights on a multi-label network. Our proposed HydREnet combines the strength of the architecture shown. The weights of the already trained multi-label network serve as the backbone. Thus, the stamp benefits from the low-level feature information of each defect class. Individual retraining of the 4 binary heads enables targeted composition of the class-dependent high-level features. For a comprehensive evaluation, we first compared the performance of the different network architectures. There is no significant difference for the strongly represented classes. However, the HydREnet is particularly convincing for the minority classes. In a second step, we compared the network architectures in terms of their training complexity. This evaluation is crucial for us as we have a dynamic environment due to the continuous technology shrinking and the highly manual process. In the left figure, we compared the number of trainable parameters of each architecture. The HydREnet saves parameters by limiting retraining to 1 head rather than an entire network. The multi-label network has only few parameters but has no option to retrain individual classes. This is a clear disadvantage regarding the training flexibility. In the figure on the right, we have multiplied the number of trainable parameters by the number of epochs. We divided this value by the associated value for the HydREnet in order to obtain a training time ratio that is independent of the GPU used. The training time of the HydREnet is significantly shorter than for the binary architectures. In summary, we proposed the first defect inspection framework in reverse engineering with an underlying network architecture, the HydREnet, that is strongly tailored to the requirements of the given dynamic environment. We have shown a cost-benefit analysis on 2 other industrial datasets in the paper.